Hi everyone, welcome in this last video on the series on implicit regularization, benign interpolation, and benign overparametrization. So the topic for today will be benign overparametrization. So what have we seen so far? What we have seen is that gradient descent induces some implicit regularization in the interpolation regime. And in particular, so we have been focusing a lot on the linear regression, and we have seen that if we do gradient descent on the least square problem, then we end up with an estimator which has a variance which is not too high when we are in high dimension, and this is thanks to the regularization of gradient descent. But at the same time, maybe it will suffer from a large bias. So the question is, what does it tell us about overparametrization? So what we have in mind when we talk about overparametrization corresponds to a case where we have much more parameters than the sample size. And this is typically what will happen when you have fitting some neural networks, which are very complex with many hidden layers, many neurons, and you have only a small sample size, which is much smaller than the number of parameters. Well, if you look at your linear regression here, what you have is that so the number of parameters, which is the dimension p of beta, this is also the input dimension. So p is both the input dimension and the number of parameters. So we cannot disentangle the effect of high dimensional input from the effect of having many parameters. In order to understand the effect of overparametrization independently of the effect of high input dimension, we must look at some more complex models. So before doing this, I want to do a first short remark. I want to emphasize on the fact that overparametrization is not new at all in statistics. This is really something that is very classical. When you do non-parametric regression, like this, what are you doing? So you say that you have some y, which is a function of some x plus some noise. And you say that this function is some function, for example, in some Sobolev space. So you have a model which is the space of all Sobolev function. And you know that Sobolev space have infinite dimension, so it's much larger than the sample size. So you are really overparameterized. So the question is, what is new in the practice in neural networks? What is new is that when you are in non-parametric statistics, we use some explicit regularization. And I want to give an example for this. For example, if you want using cubic splines, typically what you are doing is to use the solution of a least square problem, which is regularized by the mean curvature. So you are looking at all the function so that you can integrate the square of the second derivative. So you minimize over all this function the fit of the data, which is given by the square, and you penalize by the mean curvature of your function. And this will prevent you from having too wavy solutions. So if you take a lambda, which is too small, you will end up with a solution which will be very wavy, and this will prevent you from this. So what is new is that in the neural network practice, some people use very complex neural networks with many layers, and they just do a plain gradient descent or stochastic gradient descent without any regularization. So some people are using regularization like weight decay or dropout, but some people just use plain gradient descent or stochastic gradient descent. And it turns out that it works well. So the question is, why does it work? And I think that, well, you should know it after 3 videos. It will work thanks to the implicit regularization of gradient descent. And what we do is to illustrate this on a simple example. And our simple example will be a neural network with one hidden layer. So this is something that we usually represent like this. So this is a function which input dimension d that output a real number and which is of this form. So you have an activation function which is simply a function from R to R. So very popular function is the ReLU. And what you will do is to take a linear combination of this quantity, which are some scalar product of x with respect to some vector omega j. Okay, so what you do is you take some scalar product between x and, for example, omega 1, you apply phi, and then you do this for all your omega j, and at the end, you take a linear combination of this, where the combination is with respect to beta j. So we denote by m the number of neurons here, and what will be the overparametrized regime? It will correspond to the regime where we will let the hidden layer, the size of the hidden layer goes to infinity. So we take an infinite number of neurons. But we will not touch to the input dimension. The input dimension will stay fixed, but we will have a very large hidden layer. This will correspond to the overparametrized regime. And here you see that input dimension does not change, so we have disentangled the two. So what will be our setting? So we'll consider binary classification. So we have some learning points, some xi, which is in RD, and some yi, which x value -1 or +1. And we had n observation for the learning dataset. So we consider loss function into a convex loss function, and we will apply learn the parameters by applying gradient descent on the empirical loss. So you take the empirical average of the loss on the learning point. And typically, what you can think is that the loss is the logistic loss. So I want to emphasize on one point is that, okay, L is convex, but because this is not linear, this is not convex. And in particular, since this is not convex, it's not very easy to understand how gradient descent behaves on this function, which has maybe some strange behavior. Right. So now we want to understand what's going on when the hidden layer goes to infinity, the size of the hidden layer. So we let m goes to infinity here. So what you can imagine is that when m goes to infinity, the continuous version of this will be to replace this by some integral with respect to some measure mu. And mu will be a probability measure because this sums to 1. So let us do this. So we let m goes to infinity, which corresponds to this parametrization. So now the parametrization will be by this probability measure mu in RD plus 1, and we will integrate beta phi of omega scalar x against this probability measure mu. And I will use the short notation theta dot to represent beta omega. I will also write this function as phi of theta and x, in order to have a simple notation, so that we can represent this function as simply the integral of this function against the probability distribution mu, where I use the bracket in order to represent integration. And what you notice is that now, since so my parameter is mu, and you notice that here now I have something which is linear in this parameter. So I have something which is much nicer. And in particular, if I look at my empirical loss, this is something which now is convex because L is convex. So at least when we look in the overparametrized regime where m goes into infinity, you see that overparametrization helps for the optimization landscape. We will have a better optimization landscape. And the question is there a statistical price for this? Because maybe the optimization landscape is better, but statistical behavior is not very good. So I will discuss briefly this example, this case, on a simple example where we choose for phi the ReLU function or for L the logistic loss. And what we will do is to reparameterize everything by using the fact that this function is homogeneous. So if I take some theta and I multiply by some lambda, which is strictly positive, okay, so lambda theta is the vector lambda beta lambda omega, then what I have, so here I have lambda beta and I have phi of lambda omega scalar x. Now we use the fact that the scalar product is linear, so I can move the lambda out on the scalar product. And I use that phi is homogeneous, so I can move the lambda outside of phi. So I have lambda square times this function, which is nothing but my function evaluated at theta. So what it means is that if I want to understand this function, in this case when I have the ReLU activation, well, I don't have to care that much about the norm of theta because it will just be a factor in front of it. So essentially what I have is to understand the direction of theta. So for this reason, we use a parametrization, or we parameterize theta by some u, which is in the sphere, and some lambda, which represents the norm of theta. So by doing so, by using this parametrization, I can write my function, which is here, as the integral over lambda positive on u on the sphere of dimension, so in Rd plus 1, of this quantity. And now you know that phi of lambda u is lambda square phi of ux. So what you can do is to integrate first over lambda, and you see that this term does not depend on lambda. So you can put it out of this integration here. So I will have phi, I will have my lambda square, and now if I integrate over lambda, this gives me a positive measure on the sphere in Rd plus 1. And I will call pi mu this sphere, this measure, sorry. So this measure is positive, so it is normal probability distribution. But what is nice is that it acts on the sphere. And as I said, what is important for the behavior of this function is to understand what's going on the sphere, because the norm is something which is a factor, and the mass of this function, which simply tells you how much you put in the direction. Okay, so here I have moved from an integral on the whole space to an integral on the sphere. And p mu is this measure. Okay, so let us look at the interpolation setting. So in terms of overfitting, I should write interpolation here. So what is interpolation? The interpolation is when you can, for all your learning data set, predict yi by taking the sign of your function evaluated at xi. But it turns out that any Lipschitz function f can be represented by some f mu. So as long as no point xi has two different labels, so as long as you don't have two different data points which have the same x but two different labels, then you will find a mu such that you can have a perfect classification. So interpolation is something which is very benign in this case. This is a very mild assumption to assume that it is possible. It simply means that you don't have two data points which have the same x but two different y. All right, so now what we will do is an analysis which is very similar to what we have done for the logistic regression. So we consider gradient descent, And we assume that, so we are doing gradient descent on this parameter mu here. And we assume that after some t steps, I have something that perfectly fits the data, which means that yi and f mu at t of xi are of the same size. And I remind you that I can represent this function by this integral here. And just to have more readable notation, I will denote this q of mu at t by simply mu at t. Okay, so p hat t is this for mu hat t here. All right, so now we'll do exactly the same reasoning as for logistic regression. So we use the fact that the logistic loss is decreasing. So if you want to make your empirical loss goes to zero, you just have to increase the mass here of this measure. So typically what will happen is that when you perform your gradient descent, the mass will go to infinity. And since the mass goes to infinity, so this which goes to infinity, so we can use the fact that the logistic loss is essentially the same as the exponential. So your empirical loss is essentially equal to 1 over n, the psi of the I of the exponential minus this quantity. And as we did for logistic regression, we will divide and multiply by the mass of the measure. Okay, so this denotes the mass of my measure p hat t. So why are we doing so? Because this is something that will be a probability distribution. All right, so it does not have a mass that diverge, and this is the term that will diverge. So as we have already discussed, when you take the sum over I of something that goes to infinity, and here you have some coefficient, let's say alpha I, the dominating term will be those for which alpha I is the smallest. So this sum is essentially equal to the number of I for which here you achieve the minimum divided by n, because you have a 1 over n, times the exponential of this term, where you have this mass that goes to infinity, and here you have the margin of the predictor associated to the probability distribution p hat t divided by its own mass. So what you can imagine is that what gradient descent will do, so it will send this to infinity, but it will also try to minimize this, because you want to go farther as fast as possible to zero. So it tries to maximize this quantity, and you can imagine that for t large, gradient descent will try to make this probability distribution as close as possible to this probability distribution, which maximizes the margin over all the distribution, probability distribution on the sphere in dimension d plus 1. And this is simply this function here. And it turns out that, okay, under some mild assumption, this is actually what's going on. If you have convergence, you will have such a convergence. All right, so we see that in this model, which is more complex, we again have some implicit regularization from gradient descent, which will correspond to some max margin. So we maximize some margin. And the question is, what is the benefit for this? Well, once you show that you have some max margin classifier, you can use some classical results that I will not describe here, which tells you that your classifier will have some nice statistical properties. And in particular, what is possible to show in this case is that the classifier is able to adapt to low-dimensional structures. And if you want to see more about this, I refer to the original paper by Lenaik Shiza and Francis Bach from 2020. This is a very nice paper. So in this case, what we have is that implicit regularization of gradient descent plus overparametrization gives me first a nice optimization landscape, but also I will have some nice statistical behavior due to the fact that I have some max margin classifier. So I will not discuss more overparametrization. What you have to know is that this is something that okay, is a bit understood in simple model, but for much more complex model, the situation is much more complex and it is not very well understood. But I hope that at least by looking at this simple example, so linear regression on the one hidden layer network, you grab some intuition on why it is possible to have some good performance, even if we have a strong overparametrization. So what are the take-home message from this series of lectures? So the first message that I have repeated so many times is that in the interpolation regime, gradient descent has a regularization effect by selecting some specific interpolating solution. In addition, what we have seen in videos 2 and 3 is that when the input space is very large, you will overfit, but only on a small region of the input space. And so this overfitting will not have a big impact in the prediction risk. And actually, what will have a big impact is the fact that most of the time, when you will have a new learning point, you will be not so correlated to your learning data points, and you will predict by something which is close to zero, at least for the high dimensional part of the signal. And finally, as we have shortly discussed today, overparametrization can be harmless and even beneficial, just thanks to the optimization landscape. So to conclude, there are still many things to be understood, but I hope that this series of video has given you some insights of what's going on in this high dimensional space and in this overparameterized regime. So see you later for some new series of video.